In order to prevent global warming from reaching 1.5 degrees, it's estimated that the next 10 years are crucial for us to collaborate across sectors to remove and prevent carbon pollution, which is also known as greenhouse gases. An incredibly interdisciplinary open data project called Climate Trace is presently led by 10 entities and former Vice President Al Gore, and is collaborating with over 50 organizations to come together and help detect where carbon pollution is presently coming from by country and even by industry, using satellite images and machine learning. Soon, it will transparently publish where pollution arises from a particular factory, a coal plant, an agricultural field, an animal farm, etc. The intention behind creating this global inventory of emissions is to help policymakers, industry operators, and even consumers who may unknowingly be investing in high-polluting organizations and take actions quickly to prevent a climate crisis. Because the energy sector is currently a top focus, in this episode, we walk through how to generate a geo-spatial classification model that passes the image of a coal power plant from a satellite called Sentinel-2 and tells us whether that plant is on or off. Thanks to data, today we can understand our natural world with far greater richness than ever before by orders of magnitude. This now empowers us to build amazing apps that can help us solve complex social and environmental challenges. And so in this series, let's build an app together. Meet Gavin, who is Executive Director at Wattime, which is a nonprofit that helps the public understand how clean is the electricity I'm using right now, using technology. Historically, it's been challenging to measure this.
The global state of the art mostly is self-reporting, just asking emitters how much they emit, and in some cases having extremely expensive on-site equipment at individual power plants and factories. A couple of governments around the world, but very few, have open power plant monitoring, and they monitor their heaviest sources of emissions and provide that data free to the public. For most sources of emissions around the world, there is no equivalent system. And so it wasn't the case that we could just add up all of the open data and process that into a global emissions system. We actually needed to go out and create the emissions databases that we were aggregating to have a sense of global emissions.
Climate Trace's web app and dataset uses publicly available satellite data from Earth Engine as well as privately owned data. And all the compute processing and classifying of the 59 trillion bytes of data from over 11,000 sensors that come from hundreds of satellites is done on Google Cloud by using products such as TensorFlow and Vertex AI for training and labeling data, BigQuery and Earth Engine for data analysis, and Kubernetes Engine for container management, just to name a few.
Without Google, this project really would have never happened. We submitted a grant application for what we thought was a little bit of a pie-in-the-sky moonshot. We thought if this worked, it would be amazing. Google took a really big bet on a project back when it was just an idea. They gave us a generous $1.7 million grant to make the project possible. And then they doubled down. They said, you know what, we really want this project to succeed, and we're going to send 7 engineers full-time for 6 months to help accelerate this team of scientists to make sure the machine learning and the data engineering really are successful. They then further doubled down to support the coalition as this project matured, growing from an initial idea around power plants to the new Climate Trace concept of monitoring all GHG emissions.
I am beyond impressed and very proud by this project, and send a warm-hearted shout out to all the volunteers and organizations who have made this idea become reality. For those of us equally interested in working with AI and satellite imagery, let's go a bit deeper on how we could approach this problem. Let's start with understanding our inputs and outputs. Our input data comes from Sentinel-2, which is a satellite owned by the European Space Agency. Multispectral images of the entire planet are taken every 10 days since 2015. Every pixel in these images approximately covers a 10 meter by 10 meter area. When working with satellite data, each input image has dimensions of width, height, and bands. Bands are measurements from specific satellite instruments for different ranges of the electromagnetic spectrum. For example, Sentinel-2 contains 13 spectral bands. If you are familiar with image classification problems, you can think of the bands similar to images as red, green, blue RGB channels. However, when working with satellite data, we generally have more than just 3 bands. As for outputs, in this example, the output is a single number between 0 off and 1 on, representing the probability of that coal plant being on. Next, let's move on to building a dataset. Climate Trace went through the labor of love of labeling lat-long locations of coal plants that correspond to Sentinel-2 images and shared it as a CSV. Each coal plant's location is on or off at different times. Next, we use Earth Engine to get the band values for a patch of pixels given their lat-long timestamp and on or off label from each row of the CSV file. We basically view the band values as the data and the label as the answer. From this, we randomly split this data into training and validation datasets and save them as TF records in cloud storage. For this case, we split it into 70% training and 30% validation datasets. This means the model studies and learns from the training dataset, while the validation dataset is used like an exam to make sure it's learning to generalize to data it hasn't seen before. Next, we use Vertex AI, Google's machine learning platform, to train and validate the model. We use a convolutional neural network, which is an ML technique that works well with image data. It receives a patch of pixels where the power plant is at its center. And as a friendly note, each pixel in Sentinel-2 is approximately 10 meters, so we decided to use a padding of 16 pixels around the plant. That means that our 33 by 33 patch is around 330 meters by 330 meters. Because of this, our training data is a consistent patch of 33 by 33 pixels, and the model returns the probability of the plant being on. Once we're happy with our model, it is stored into cloud storage as well. And in order to use that model to make predictions of coal plants, we deploy it on Cloud Run and make it a predictions service. And when done, we celebrate with a dance party. So what's next? If you would like to review this process in greater detail, in the description below, I have included the link to an interactive notebook with all the code used to build a sample, written by Nikita, a super passionate peer of mine. You can also find a blog post and several helpful resources too. And community, I'll leave you with a fun fact from Gavin about the project before we end. And if you found this content helpful, you can subscribe or leave a comment on other AI for good use cases you may have in mind. Cheers!
One fun surprise about this project is I didn't know how much the satellites that orbit the Earth today are mostly designed for maps. So that we can all drive where we need to go, nearly every satellite has been designed to land at about 11 a.m. overhead. Problem is, what if you're trying to see the emissions of something that doesn't happen at 11 a.m.? We've had to call increasingly obscure agencies around the world of various countries that happen sometime to launch a satellite that's good at seeing things at night. And we've gotten to know just how many satellites are designed to see things right before noon.